Folks, I'm Marcus from UTAS. I'd just like to say I do not own a Tirana, nor have I ever owned a Tirana. Okay, on with the presentation. I just want to double check. So this is our team. How do we make it go forward? That button? That button. Yeah, so this is our engineering team that we have at UTAS, led by Simon Edwards, our rather brilliant research engineer. And I just want to say up front that everything that we've done and everything we're doing has been guided by our partners and our industry groups. The technologies that we've developed are truly co-designed, and some of them are approaching that last stage of getting back into the hands of the farmers, the technologies that they helped us conceive. And that'll be the final step in where we want to go with what we've developed. And those groups are listed here. We have a range of technologies, or animals as people call animals in my zoo, including the bandicoot, bilby, quoll and the AI hydro. Firstly, the bandicoot. We heard from farmers that they don't have the type of soil moisture monitoring technology that they want to be using. They're using the technology that they've got available to them now. And what we heard was that they wanted tools, not instruments, and they wanted mobility. They wanted to be able to go into a paddock and measure soil moisture where and when it suited them, not having a probe permanently installed in just one location. And so what the farmers told us is that they use a shovel to do that now, and what they really wanted was a smarter shovel. And over time, that smarter shovel has morphed into the bandicoot. And the bandicoot is a combined sensor system that's measuring soil moisture, penetration resistance, and also apparent conductivity. Apparent conductivity, think back to the old EM38 with the old orange planks. It's a bulk measure of soil texture, density, moisture, salinity. So it's measuring that concept in the soil, but because we're using a particular multi-frequency approach to our analysis, we should be able to separate that out. And so there's a whole batch of research to be done on understanding how we can use it to predict clay content, mineralogy, some of these other factors that we're hoping to do. It's handheld, it's mobile, it's got GPS, it's mapping, navigation, and it's going to have really sophisticated software that you can view your results on your phone or back at your computer in real time. It's easy to operate. Pick up the tool, press the button, stand on it. It actually pushes in at a constant rate, out again, takes all the data, and it's then displayed to you in the field and directed to your phone, and can upload directly to the web or has Bluetooth connectivity to your phone. In this last project, this last phase, we've actually really advanced the commercial development of the bandicoot. It's been through the beanstalk process. We've also had a major study done by CSU on the marketability of it and how it fits within different farming systems by CSU. And the outcome of that is that it's really a tool designed to the horticulture sector. Short-rooted crops, cultivated soils, high irrigation rates, high input rates, high-value crops. And what we'd also like to do is articulate a different version for the rain-fed crops that would be vehicle-mounted. That's what we'd really like to see as well. So that's our bandicoot. Here's our quoll. So the quoll has sort of left the stable and is now being co-developed under other programs beyond the CRC. It's an e-nose designed for sampling soil gases and understanding, trying to untangle the understanding of soil microbial function. All our existing tests in soil microbiology are point in time, point in space. This is the only continuously measuring approach that's available, and they're relatively cheap. And we're already using it quite productively. You can see from these trials here, oh, by the way, it measures basically reducing gases, oxidising gases, volatilizable organic carbons, as well as CO2 directly, soil moisture, temperature and humidity. So it's this suite of sensors. And you can see here just from the CO2, we can see land management effects of compacted and non-compacted soil. We can see differences in crop type. And you'll see here differences in crop type falling out of the data and differences in soil type. So it works really well at the moment where you've got a paired comparison. Is this different to that? Are the microbes behaving differently here than where they are here? And that's where it's working really well at the moment. The next technology I'd like to talk about is AI Hydro, which is being developed by my rather brilliant PhD student, Shenting Zhang. You know, Pete Dalhouse referred to those 800 million soil moisture measurements, and yet we've got almost, well, very, very few measurements of soil physical properties in this country. Shenting's PhD takes those soil moisture measurements and derives the soil physical properties of the soil in which that probe is installed. She's created an intelligent sensor. It understands its own environment. And from that, we can do stuff like parameterised models like APSIM. We can better predict irrigation deficits. But I'll let Shenting tell her story because she's coming up next and I don't want to steal her thunder. She wouldn't let me anyway. And on to the bilby, the last of our technologies that we're developing. We heard from farmers that they had a hassle with soil moisture probes. They loved the data, they loved what they learnt, but they were a hassle. And the two hassles they talked about was them being damaged by being run over by tractors, eaten by cows, damaged by pests, machinery, and the hassle of having to go and spray a paddock and steer around all these solar panels and data loggers and bits in the field. So the solution was, let's put the whole lot underground and send the data through the soil. And that's what we've been working on. So this second phase of the bilby's funding, we commenced a trial with a potential industry partner, Centec. And they were great. They came on the ground with us. They put boots on the ground from day one of exploring a partnership arrangement with us. And there's nothing like boots on the ground, as you guys know. And what we found was when we buried our bilbies at 30 centimetres and it got wet, we got unreliable results. It was possible to send data, but we weren't continuously getting data. And Centec, interacting with Centec, we finally managed to develop what we needed to do in terms of performance to have a truly marketable product. And that was 95% of data sent and received on first attempt. Being able to send data from 30 centimetres depth in a wet soil through a large biomass crop to at least 150 metres away. And that's quite a task. So that's their requirement of us. And having that line in the sand means we've got something to engineer to. We found burial mattered. If you don't bury it with the local soil and you use the sand of a known dielectric constant, you can tune your antennas and stuff much better and we get much better reception. So burial environment is important. But then we discovered we had an issue with biomass. And you can see here, this is the strength of our signal dying as the crop grew. And when it got below that threshold, we lost the lot. So biomass became important because the biomass held moisture from the irrigation. And you can see the individual irrigation events, this up-down pattern. Holds water, we can't shoot through water very well. So we went back and rethought about, come on, behave. We rethought about our, there we go, had to happen, our antenna that we developed in the first project. We remodeled it, we went back to field trials with it, and we started exploring alternative antenna prototypes. And this is within the last 4 months of the project. So all of a sudden we hit panic mode. We dropped development of the Bandicoot and put all our resources into trying to solve this problem to meet that industry requirement. And as you can see here, we now have really targeted transmission. And we put that into trials, and our trials locally showed that we were getting improved performance. We even tried modifying the enclosure, and what we found is we could. It's not just the antenna, it's the antenna and the enclosure system together. It's how the two bits come together, modified our success in transmission. And then we put that into a trial, or I should say Centec put that into a trial back at their base in South Australia under a very big Brussels sprout crop. And what we found is over to Mark, for you to tell your side of our story.